The moment an aircraft penetrates a dense cloud bank and loses the outside horizon, the pilot is immediately subjected to the threat of spatial disorientation. Without a visual reference, human vestibular senses quickly feed the brain false sensations of movement. Simultaneously, the magnetic compass becomes erratic and unreliable the moment the aircraft enters a bank. To survive, the pilot must transfer absolute trust to three specific panel instruments: the direction indicator, the artificial horizon, and the turn indicator. These instruments are mechanically reliable, but they are not flawless. If any of them manifest physical errors that the pilot does not immediately recognize and understand, the resulting corrective inputs will lead to a loss of control. Surviving instrument meteorological conditions requires a strict mechanical reliance on the physics of spinning gyroscopes over human instinct. Inside the panel, each of these three instruments depends entirely on a single spinning gyroscope. If you are preparing for your exams, subscribe to Captain Aero for daily DGCA theory breakdowns. Mastering these instruments means understanding exactly how a freely spinning mass exploits two specific physical properties to output accurate two-dimensional data on the flight panel. We start with the core mechanism, a standard unpowered gyroscope rotor suspended in a three-dimensional frame. Once spun up to speed, this mass exhibits rigidity in space, resisting any force that attempts to change its plane of rotation. This gyroscopic inertia is mathematical, scaling directly with the physical mass of the rotor and its rotational speed. However, if an applied force is strong enough to overcome that rigidity, the gyroscope exhibits its second property, precession. When a force is applied to the spinning rotor, the gyroscope does not tilt in the direction of that force. Instead, the resulting tilting movement occurs exactly 90 degrees away, in the direction of rotation. To apply these principles to the cockpit, we must determine which property is best suited for directional stability versus rate measurement. Because the direction indicator requires a fixed reference that stays still while the plane turns, it utilizes rigidity. Conversely, because the turn indicator must convert a turning force into a readable needle deflection, it relies on precession. Simply changing how the gyroscope's spin axis is physically oriented inside the instrument case determines which of these two physics properties it can exploit. The direction indicator, or DI, is the pilot's primary heading reference. It is engineered to harness rigidity in space. Inside the DI, the gyroscope's horizontal spin axis maintains a fixed orientation in space while the aircraft turns around it. Because this rigid horizontal gyro lacks directional seeking ability and is blind to magnetic north, pilots must manually synchronize it with the magnetic compass. This constant synchronization is required because of a class of instrument errors known collectively as wander. Apparent wander is an illusion caused by the Earth rotating beneath the fixed gyroscope. Drift is zero at the equator and maximum at the poles. The DGCA formula for this drift is 15 times the sine of the latitude, yielding degrees per hour. The second error is transport wander, which occurs because the aircraft is physically moving its local meridian over the curved surface of the Earth. Finally, real wander is the physical degradation of accuracy caused by unavoidable mechanical friction in the gyro's own bearings. The combination of apparent, transport, and real wander results in a total navigational drift that forces the mandatory 10 to 15-minute compass synchronization intervals. The artificial horizon, or attitude indicator, provides the reference for true vertical pitch and bank during instrument flight. In this artificial horizon cross-section, the gyroscope spin axis is strictly vertical. The instrument casing pitches and rolls with the aircraft, but the vertical axis remains locked. This rigid axis controls the horizon bar, keeping it stable as the miniature aircraft moves around it. However, specific aircraft maneuvers can trick the instrument's internal erection mechanism, inducing false readings. The first is turning error. During a prolonged, coordinated turn, centrifugal force is introduced. Normal gravity intersects with this centrifugal force, creating a false apparent vertical vector that tilts the mechanism. To the pilot, this manifests as a false bank indication. The second is acceleration error. When the aircraft undergoes rapid linear acceleration, inertia forces the erection mechanism to pitch the horizon bar. This creates a specific illusion. Acceleration registers as a false nose-up attitude, while deceleration reads as a false nose-down attitude. Additionally, a standard conventional artificial horizon operates within absolute mechanical limits, typically 60 degrees of pitch and 110 degrees of bank. Exceeding these limits causes gyro topple. The gyroscope violently tumbles out of its stable position, rendering the instrument completely useless until it eventually re-erects. Trusting the artificial horizon during prolonged extreme maneuvers or rapid acceleration will induce spatial disorientation and incorrect control inputs. The turn and slip indicator falls into a different category. It abandons rigidity and relies exclusively on precession to measure movement. In the turn indicator, the horizontal spin axis is perpendicular to the aircraft's longitudinal axis. Yawing applies a rotational force directly to the gyro mounting. This specific force causes the gyro to precess, deflecting the panel needle proportionally to the exact rate of the turn. This allows us to measure a standard rate turn, known as rate 1, which is precisely 3 degrees of rotation per second. At rate 1, a full 360-degree turn takes exactly 2 minutes to complete. For a rate 1 turn, the required bank angle changes based on speed. The formula is true airspeed divided by 10 plus 7 degrees. A slow aircraft requires a 15-degree bank, while a faster aircraft needs 30 degrees to maintain the 3 degree per second rate. The bottom half of the instrument houses the slip indicator, also known as the balance ball or inclinometer. It uses simple fluid dynamics to verify coordinated flight. If the ball rests in the center, the turn is coordinated. If it swings to the right, the aircraft is slipping due to too much bank. If it swings to the left, it is skidding from too little bank. To correct uncoordinated flight, pilots apply a strict universal rule: step on the ball. Apply rudder pressure on the side the ball is resting. The turn and slip indicator is vital because precession reliably translates invisible yawing forces into exact mathematical rates of turn, preventing spiral dives when the horizon is lost. To consolidate for the exam, we map the 3 instruments to their mechanical foundations using this matrix. Column 1, the direction indicator, utilizes a horizontal rigid axis locked in space, subject to apparent wander errors calculated by 15 sin L. Column 2, the artificial horizon, utilizes a vertical rigid axis locking pitch and roll, limited by acceleration illusions and mechanical topple. Column 3, the turn indicator, harnesses precession with a horizontal perpendicular axis to measure exactly 3 degrees per second. Flying safely in instrument conditions requires active anticipation of these underlying mechanical limits, rather than passively reading lines on a panel. Our next DGCA theory breakdown covers visibility and fog. Click the video on screen to continue. Developing a precise mental model of these mechanics allows a pilot to interpret instrument readings through their physical limits, a prerequisite for both safe IMC flight and a passing score on the DGCA examination.